Hi friends, welcome back to a new session. In this session, we'll discuss calls for drop in terminal voltage of alternator and armature reaction in alternator. Okay, so let us see causes for drop in terminal voltage. Causes for drop in terminal voltage. So terminal voltage of one alternator. So it is we are discussing it in the synchronous machine chapter. So cause for drop in terminal voltage of alternator. You can say alternator. Okay. Right. Now see, we know generally in alternator armature winding is in a star connection. This already we discussed. Okay, so armature winding should be in a star connection. Armature winding should be in star connection. Okay, star connection. Now, whatever field winding is there, to that field winding, we know what is the purpose of field winding. Field winding is used for excitation. So this field winding, if we give DC supply, so some DC supply is current to the field winding. So IF current is flowing. So field current is, some current is flowing through the field winding, so that flux will be created. I already told you the process of sending current through field winding and creating magnetic field is called excitation. That means indirectly field winding is used for excitation. Okay, and this is what I can say armature winding, field winding. Okay, and generally we'll be using in case of synchronous machine, we'll be placing armature winding on the stator, field winding on the rotor. So already we discussed. So you can place armature winding on the rotor, field winding on the stator also. So both arrangements are possible, but because of some advantages, I told you armature winding should be placed on the stator and field winding should be placed on the rotor in case of large size alternators which we are using in a power system. Okay, power generation alternators. So generally synchronous machine means both arrangements are possible. You can place armature winding in the stator, field winding on the rotor. You can place field winding in the stator, armature winding on the rotor. But because of some advantages, generally in large size alternator, we'll be going for placing armature winding in the stator, field winding on the rotor. This already we discussed it. Okay, right. Now let me connect some load here. I told you we are placing armature winding in the stator, field winding in the rotor. No, so let me indicate this indication means we are placing field winding in the rotor in the direction of your prime mode torque. Okay, right. And let me connect some load here. Let me connect some load. Okay. So yes, first of all, because of excitation, so let us assume that under no load condition, because of excitation, that means because of sending current through field winding, flux will be created. Okay, and because of that flux, and here armature currents are there, rate of change of flux linkage will be there, so the EMF will be induced. Let me call that EMF as EMF. I can call it as EMF E is induced. EMF E, or I can say easy induced, or I can say E whatever. And suppose if load is connected now, so definitely you know that armature current IA is flowing. So this IA is nothing but I phase. This I phase is nothing but IL. Because in star connection, line current is equals to phase current is equals to that is equals to armature current. To be frank, this IL can be called as load current also, right? Load, because here it is load, so I can call this IL as the load current. Okay. Now here load voltage can be taken as V. Okay. And you just tell me EZ is equals to, means I can call this EZ as generated voltage. EZ equal to load voltage V plus so many drops are there. What are those drops? So through this armature winding, if current IA is flowing, so armature winding will be have some resistance RA. So IA RA drop will occur. So let me call it as IA RA. This is drop due to armature resistance. And because of leakage flux also you will be having some drop. That drop can be shown with JIAXL. JIAXL. And because of armature reaction also you will be having some drop. Let me call it as IAXA. IA. Observe it clearly. Armature resistance drop I just shown with RA. Leakage flux drop and armature reaction drop I'm just showing with the symbol reactance X. Why? It's very simple. Because of something, if you are having only drop, that drop we have to show with the reactance parameter. Because of leakage flux and because of armature reaction, you will be having only drop, not losses. That's why you have to show that drop with reactance parameter X. Because of armature resistance, in addition to drop IARA, you will be having loss will come into picture IS for RA. That's why let me represent that drop with the resistor parameter R. Is it clear? That's the reason why I'm just showing this drop with the resistance IARA and this drop with the reactance symbol XL and XA. Here nomenclature I can call it as EZ can be called as generated voltage, V can be called as load voltage or terminal voltage, IA can be called as armature current or indeed nothing but armature current, or I can say load current, because in the star connection I phase equals IL equals IA, so this armature current itself becomes the load current. And whatever RA, armature resistance, and here XL means what? Leakage reactance. What is that? Leakage reactance. XI means armature reactance. Armature reactance. Armature reactance is used to represent drop due to armature reaction. Leakage reactance is used to represent drop due to leakage reactance. Drop due to leakage flux. Armature resistance is used to represent drop due to armature resistance, right? And from this, tell me, if you want me to write V equal to, I can write this one, V equal to EZ minus IARA minus JIAXL minus JIAXA. What is your heading here? Calls for drop in terminal voltage. Do you think that your load voltage, or I can say terminal voltage, V equal to EZ? No. It's ideal case point of view, I can say that V equal to EZ. Whatever generation is there, that will be equal to load voltage. But practically, you'll be having so many drops. No. What are those drops means? The terminal voltage or load voltage V equal to EZ minus these are the drops. These are the drops. Tell me what about this one? What about this one? This is drop due to armature resistance. Drop due to armature resistance. Okay. So this will be around, I can say 0.01 per unit. And what about this IAXL? IAXL means what? IAXL I'm asking. Drop due to leakage reactance. Drop due to leakage reactance. Drop due to leakage reactance. So it will be around 0.15 per unit. 0.15 per unit. And what about XA? IAXA? IAXA is nothing but drop due to IAXA. Drop due to armature reaction. Drop due to armature reaction. Drop due to armature reaction. Drop due to armature reaction will be around 0.84 per unit. 0.84 per unit. Okay, is it clear? Now if you add, guys, if you add 0.01, 0.15, 0.84, it will be 1 per unit. So obviously you can understand clearly by seeing this. Tell me, so what is the most dominated drop here? So you can see this armature resistance drop is very less. It's almost a negligible 0.01 per unit. It's very less. And what is the drop which is more dominated here? It's clearly visible that armature reaction drop is more dominated. It will be around how much? 0.84 per unit. 0.84 per unit. So this is what I can say cause for drop in terminal voltage. And let me go for armature reaction. Why means I told you among these three drops, which one is more dominated drop? Drop due to armature reaction is more dominated drop. So let me keep heading armature reaction. Let me discuss armature reaction here. Armature reaction. Armature reaction. It's very simple. Observe clearly. See, armature reaction is definition I can write like this. Effect of armature flux. Effect of armature flux. Nothing but phi A on main flux. Nothing but pi m is called armature reaction. Effect of armature flux on main flux is called armature reaction. You observe, guys, initially whenever excitation is given to the field winding, if there is no load, okay, so I don't have any, so whenever there is no load, because of this excitation, I'll be getting only easy. Because of this easy, we won't get IA current, because here under no load condition, no. If there is no IA, what about pi A armature flux? Armature flux is due to armature current. Whenever armature current is 0, what is armature flux value? 0. That means under no load condition, do you have any armature reaction effect? No. Because armature reaction is what effect of armature flux and main flux is called armature reaction. Under no load condition, IA is 0. Armature current is 0. That means armature flux will be equal to 0. Therefore, there is no effect of armature reaction under no load condition. So let me give the point here. Note. Okay. Effect of armature reaction is absent. Effect of armature reaction. Let me write simply AR. Armature reaction. Let me call it as AR. Effect of armature reaction is absent. Effect of armature reaction is absent under no load condition. Under no load condition. Why? Since IA equal to 0, pi A equal to 0. That means, tell me, armature reaction exists, effect of armature reaction exists only under loaded condition. So let me write here. Effect of armature reaction is present under loaded condition only. And one more thing, what is that effect? Because of suppose whenever load is there, obviously because of this EEG, IA will come into picture. Because of this EEG, IA current will come into picture. Because of that IA, phi A will come into picture. Armature flux will come into picture. Effect of armature flux will be there on main flux phi m. That is armature reaction effect will be there. See guys, very simple. Effect of armature reaction depends on what? Means magnitude of the load. Under no load, IA 0, pi A 0, I can say effect of armature reaction is absent. That means effect of armature reaction depends on magnitude of the load. At the same time, it depends on type of the load. Suppose if load is the unity power factor, UPF load, you will be having one effect. If load is ZPF lag, you will be having one effect. If load is ZPF lead, you will be having another effect. If it is something like 0.8 power factor lag, you will be having some other effect. 0.8 power factor lead, you will be having some other effect. That means what I want to say is, effect of armature reaction depends on not only magnitude of the load, but also it depends on type of the load. So let me give that note here. Note. Effect of armature reaction depends on magnitude of the load, magnitude of the load, and and type of the load. Type of the load means, I told you, if load is resistive load, will be having one effect. If load is inductive load, will be having one effect. If load is capacitive load, will be having one effect. If load is RL load, will be having one effect. If load is RC load, will be having another effect. Okay, so it depends on magnitude of the load and also type of the load. We'll see, we'll take some different type of loads and we'll see what is the effect of armature reaction under loaded condition in case of alternate. Okay, first note on up to this. Right. Now let me erase this one. We had started armature reaction topic here. Now I told you it depends on magnitude of the load and the type of the load. I'll take different loads and let us see effect of armature reaction. In place of this load, first I'll take UPF, next ZPF lag, ZPF lead, 0.8 lag, 0.8 lead. Like that we'll take different loads and we'll see what is the effect of armature reaction. Right. So let me take first of all UPF load. Next, let me take ZPF lag load. Now let me take ZPF lead load. 0 power factor lag, 0 power factor lead. Next, let me take 0.8 power factor lag. Next, let me take 0.8 power factor lead. So like this, we'll take different type of loads and we'll see effect of armature reaction. Is it clear? Now, UPF, unity power factor. That means cos pi equal to 1. Is it clear? Cos pi equal to 1. See, cos pi equal to 1 means what is the value of your pi? 0. So for resistive load, your load voltage, is it clear? Your load voltage and load current will be in phase. Load voltage, load current will be in phase. Before that, before explaining all those things, let me ask you a simple question. Because of giving excitation to the field winding in your alternator, we will get main flux. Let me take that one as like this. This is what I can say main flux. Because of that main flux only, EMF will be induced in our alternator. Okay. So angle between that EMF and pi will be 90 degrees. You know that. So generally we can call this one, we can call this voltage as EZ or E, your wish. EZ, or I can say EZ or E. Okay. You can call it, you can give nomenclature as EZ or E. Let me call it as simply E. Okay. Already previously I just shown with the EZ or E, whatever. Now see guys, this vector portion, because of giving excitation to the field winding, I'll be getting main flux phi m, and because of the main flux, we'll be getting a rate of change of flux linkage will be there in our alternator. EMF will be induced in alternator. To be frank, EMF will be induced in a armature winding. So that is nothing but E. So and these two are displaced by 90 degrees. These vectors are same for any type of loads, right? Let me show here also main flux phi m and generator voltage E. Main flux phi m, generated voltage E. Here also main flux phi m, generated voltage E. Main flux phi m, generated voltage E. Is it clear? And one more thing I want to say here, very simple. See, previously I told you this is what armature winding, and it is connected to the load here, and this is what field winding. So this field winding only I had given some DC excitation. So this thing I already previously just drawn. So EMF can be called as EZ, or this EZ equals to E, you can call it as. And armature current can be taken as IA value. This is only phase current. This is only load current IL value. And this load voltage, this voltage can be called as load voltage. See guys, you know that generated voltage G and load voltage V will not be equal. Is it clear? Because E equal to V plus so many drops are there. We already discussed it. What are those drops? Armature resistance drop, leakage reactance drop, armature reaction drop. These are the drops they are having, right? So previously I told you EZ or E equal to P plus IARA plus JIAXL plus JIAXC. These things I told. Is it clear? Okay. So definitely no doubt E is not equal to V. E equal to V plus something is there. No doubt. But in this topic, we want to know only effect. I mean, because of UPF loads, what is the effect of armature reaction in alternator? Because of ZPF lag loads, what is the effect of armature reaction in the alternator? So I want to know only effect, whether it is CME, cross magnetizing effect, or demagnetizing effect, or magnetizing effect. Like that, I want to know the effect of armature reaction. So for let me assume. I mean, for some time, let me assume E equal to V. No doubt, drops will be there, I can understand that. But I need to only know the effect of armature reaction. So for time being, let me take E equal to V for some time. So please indicate here E equal to V, here also 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 E equal to V. Is it clear? Yes. Next, suppose UPF load. UPF load means, so what UPF means, it's a pure resistive load. Pure resistive load. I can call it as pure R load. Pure R load. Pure R load. What about this ZPF lag? ZPF lag means what? Zero power factor means cos pi equal to 0. Pi means 90 degrees. Here word lag is, that means current. I mean load current lags load voltage by 90 degrees. That means it's exactly, see exactly pure inductive load. So let me call it as pure L load, pure inductive load. Similarly, pure ZPF lead means I can take it as pure capacitive load, pure C load, pure C load. And what about 0.8? Means pi value means cos inverse of 0.8, which is less than 90 degrees. So I can say it's not, lag is there, but angle is less than 90 degrees. It's not a purely inductive load. It's a combination of resistance and a reactance. I can call it as a RL load, RL load. Similarly, what about here? RC load, RC load, RC load. Now let us see, guys. So if it is UPF load means load current means what here? IL can also be called as I phase. can also be called as IA. Armature current IA, load current IL, both are same here because armature winding is star connection. So please tell me, load current means from now onwards we can take simply IL or IA. So load voltage means V. So what is the angle between load current IA and load voltage V here? Cos pi 1. Pi means how much? 0. That means load current IA, load voltage V will be in phase with each other. So let me show this what a V value. Let me show in phase IA. Now what about here? ZPF lag, pure inductive load. That means load current lags load voltage exactly by 90 degrees. Lag no, 90 degrees. So this what load voltage? So load current IA lags load voltage V by an angle of how much? 90 degrees. ZPF lead. Load current IA leads load voltage by angle of 90 degrees. And what about here guys? It's a 0.8 power factor lag, no? That means definitely IA lags voltage only, but not 90 degrees. So less than 90 degrees, cos inverse of 0.8, that much value only, okay? So let me indicate load current IA lags voltage by an angle which is less than 90 degrees. Similarly here, IA leads voltage by how much angle? Less than 90 degrees. So let me show here, IA leads V by an angle less than 90. And because of armature current IA only, we are getting armature flux pi. Because of current flowing through armature winding, we are getting armature flux pi. So let me show IA and pi will be in phase in each and every case. This IA value in this direction, so let me indicate pi in this direction. This IA is in this direction, so pi will be in this direction because IA and pi are in phase with each other. Okay. And what about here? IA, pi and IA will be in phase. Similarly here also, sorry, this is the previous is nothing but IA, not pi. IA. Now tell me, this pi and IA will be in phase with each other. Is it clear? Next. Now let us see. Let us see. If you take alternator having a pure resistive load, what is the effect of armature reaction means? Very simple. This is what I can say pi m. Pi m is like this. Pi m is like this. I mean, let me use this black color flux line. And pi a is making 90 degrees with your pi m. This is what I can say pi a. So tell me what is the angle between pi a and pi m here? 90 degrees. 90 degrees. Okay, 90 degrees. So I can write here angle between pi m versus pi a is equals to 90 degrees. It's pi a armature flux is purely cross magnetizing your pi m. Cross magnetizing your pi m. So I can write simply effect of armature reaction is purely cross magnetizing. Effect of armature reaction purely cross magnetizing effect. I guess simply you can write in bracket CME. So now what is the conclusion? Alternator having UPF load at that time, because of armature reaction, effect of armature reaction is purely CME in case of your alternator. Now let us take few lag loads here. Here pi m is like this. Please try to see this aroma. And pi a is like this. Okay. That means what is the angle between your pi m and pi a here? Angle between, I am asking, pi m and pi a. 180 degrees. 180 degrees, right? So I can write simply here pi a opposes pi m. Whenever armature flux is opposing your main flux, what will happen to your net flux? It will reduce. Pi a opposes pi m, net flux will reduce. Whenever net flux is reducing, so obviously E will come down. E will reduce. What will happen to load voltage? V also will come down. Okay. So let's simply write here Net flux will reduce, E will reduce, V will reduce. Terminal voltage will reduce. Terminal voltage will reduce. Okay. Right. Now I can write effect of armature reaction is what? Effect of armature reaction is purely here flux is what? Observe clearly. Here phi A opposes phi M, net flux is reducing. That's why effect of armature reaction is purely demagnetizing effect. That means net flux is reducing. Effect of armature is purely demagnetizing effect. Demagnetizing effect. I can write it simply I can write from now onwards. I'll write in place of demagnetizing effect simply DME, right? So effect of armature is purely DME, right? Now what about the let me take ZPF for lead pure capacitor load. Phi M is like this. Right? And pi A is in phase with your pi M. Pi A is in phase with your pi M. So I can write simply like this. Pi A aids with the pi M. It is aiding. Pi A aiding with your pi M. Whenever pi A is aiding with your pi M, what will happen to net flux? Net flux will increase. What will happen to your E value? E value will increase. What will happen to load voltage? Will increase. Effect of armature reaction is purely magnetizing effect. So let me call magnetizing effect simply as ME. Okay, this is clear? Right. This is the case for UPF load, ZPF lag, ZPF lead. Now let me take 0.8 lag load. See pi A is here. Now it is having two components, right? It is having two components, one along y-axis, one along x-axis. Tell me this component of armature flux can be called as what? It is making 90 degrees with your pi M. I already told you, if pi A is making 90 degrees with your pi M, effect of armature reaction is a cross magnetizing effect. So this component also can be called as cross magnetizing component of armature flux, since it is making 90 degrees with your pi M. Now what about this flux component? It is opposing your pi M. Whenever it is opposing your pi M, I told you effect of armature reaction is purely demagnetizing effect. So this can be called as demagnetizing component of armature flux pi AD. Is it clear? Now effect of armature reaction what? It will be having partly CME effect is there, partly DME effect is there. So simply I can write here effect of armature reaction is partly CME plus partly DME, effect. Now let me take for RC load, it will be having two components, one along y-axis, one along x-axis. Tell me what about this component? It's making 90 degrees with your pi M, right? So this can be called as cross magnetizing component of armature flux pi A, can be called as pi AC, and it is making in phase with your pi M. The effect of armature reaction will be what I said. Whenever pi A is aiding with your pi M, effect of armature reaction is purely magnetizing effect. So I can write this one as pi A M, magnetizing component of armature flux. So it can be shown with the pi A M. Now tell me effect of armature reaction is what? It will be having a cross magnetizing effect is there, as well as magnetizing effect is there. So simply you can write here partly CME plus partly ME. So there is no need to write every time. I already told you cross magnetizing effect can be written CME. So demagnetizing effect can be written as DME. Magnetizing effect can be written as ME. Is it clear? Now whatever we made discussion up to now, let me keep in a table or column. so that it will be important for examination point of view to remember, right? So right. Yeah. Here, first of all, let me take power factor. This is what I can say, power factor. Power factor. And here, let me take first alternator point of view. I'll first complete this table column. Next, same effect, how it will be there in a synchronous motor. Synchronous motor. Synchronous motor. That also will write here only. Synchronous motor. First, UPF load. UPF load. Next, ZPF lag. Next, ZPF lead. ZPF lead. Next, 0.8 lag. Next, 0.8 lead. Right? Now, please. You tell me, alternator having UPF load, effect of armature reaction is what I write here. Effect of armature reaction is purely CME. So simply write here, purely cross magnetic effect, purely CME. I'm writing here purely, the purely, right? Now, effect of armature reaction alternator having a ZPF lag, DME, the two, purely DME, purely DME, purely DME. Next, for ZPF lead, purely ME, purely magnetic effect ME. Next, 0.8 lag, partly CME, partly DME. Partly. It's not purely now, it's a partly. Partly CME plus partly DME. Now for 0.8 lead, partly CME and partly ME. Okay. And for completing the table column for synchronous motor, you please do one thing. Wherever CME is there in case of alternator, in synchronous motor also please write CME only. Wherever DME is there in alternator, replace DME with ME. Wherever ME is there in alternator, replace ME with DME. First, just complete this table column. Then afterwards, I'll explain. Okay. So purely CME, yes. Let me write here also purely. I told you wherever CME is there, you have write CME only. Here purely, what I'm saying? Purely DME. So let me write here purely DME should be replaced with what? ME. Next here purely ME is there. What I have written here? DME. Here partly CME, I can write partly CME as it is, partly CME plus partly DME should be written, partly DME should be written as partly ME. Here partly CME, partly CME plus partly I should replace ME with DME. Okay. So this is very, very important table column. First complete this table column, then explain once again how it is, if it is DME, how it is ME. If in case of alternator, if it is ME, why it is DME, all this I will explain. First, note on this. Right. Here, some important points we have to discuss here. So let me give those points as notes. So very important notes here. Note 1. First point. First point in note 1. See guys, from now onwards, reactive power one term is coming. Observe clearly here. In case of alternator, if you observe clearly, okay, we are having two fluxes. One is main flux, one is armature flux. One is the armature flux. First point here, armature flux, armature flux phi A, armature flux phi A is controlled or I can say changed or whatever. Armature flux is controlled with reactive power. Very important. Please remember reactive power. This note is very important. And okay, main flux or sometimes you can call it as a field flux. Main flux phi m is controlled with excitation. Excitation is what I already told you, giving DC supply to the field winding. Okay, so by changing its excitation we can control your main flux. Main flux is controlled with the excitation. These words are very important, please. First, if you want, you can underline these words also. So in note 1, armature flux phi A changed with reactive power. Main flux phi m changed with excitation. These points you have to remember, right? Next, note 2. See, let me give a property of inductive load, or I can say lag loads. Inductive loads, or I can say lag loads, always absorbs reactive power. Lag loads always absorbs reactive power. Please let me give this point. Lag loads absorbs reactive power. Lag loads absorbs reactive power. Okay, and lag loads are under excited. They absorb reactive power, right? They are taking reactive power. Therefore, I can call it as lag loads are absorbs reactive power, and lag loads are under excited. They are absorbing reactive power. Now, let me give note 3 regarding lead loads. Lead loads delivers reactive power. And lead loads are overexcited. Lead loads are overexcited. So these words is very important. You should understand. Otherwise, it will be very difficult for you to follow. Okay. What is the property of lag loads? Lag loads absorbs reactive power, and lag loads are underexcited. Lead loads delivers reactive power, and lead loads are overexcited. Is it clear? So underexcited. From now onwards, simply wherever underexcited is there, let me use shortly UE. Overexcitation, OE. Next, what about resistive load? What's the property of resistive load? A resistive load neither absorbs reactive power nor delivers reactive power. That means it won't take reactive power, it won't give reactive power. It is neither underexcited, it is neither underexcited nor overexcited. It is simply normal excited. Okay. So let me write here. Resistive loads neither delivers reactive power, nor absorbs reactive power. Neither absorbs reactive power nor delivers reactive power. That is, resistive loads are neither overexcited nor underexcited. You can write it comma. The resistive loads are normal excited. Let me use N dot E, normal excited. This note 4 is also very important. Is it clear? Okay. Now, one thing I will give here, one small note, because some people will have some confusion here. This point is very, very important regarding examination point of view, but in my discussion I won't use this information. Okay, this point will be useful for examination point of view. Please remember clearly. Suppose, guys, what I am saying is, suppose you are having a lag load is here, and the lead load is here. Lag load, lead load is here. What I said, lag load absorbs reactive power. I am saying, right? I am saying lag loads absorb reactive power. This means lag loads are absorb reactive power. Lag loads absorb reactive power. That means they are taking reactive power. From whom? From lead loads, right? From lead loads. See, reactive power is coming. So please observe clearly. Lag loads absorbs reactive power. This reactive power is coming towards what? I am saying towards L, towards lag load. That means lag load absorbs which type of reactive power? Lag load absorbs lagging reactive power, because this power is coming towards L. Towards L means I can write simply lag, because this load is having a lagging nature, so it is absorbing what reactive power? Lagging reactive power. Okay, so let me write first point here. First point, lag loads absorbs which type of reactive power? Lagging reactive power. Why I am just giving this point means, sometimes they will ask you like this, lag loads delivers. Sometimes this arrow mark will be like this, reactive power. That means lag load delivers reactive power. It is going towards C. That means leading nature. So it is going towards C, towards leading nature. So I can write simply lag load delivers reactive power. Which type of reactive power? It is going towards the towards lead load. So I can write simply here lag load delivers. So from here it is leaving, right? It is going towards leading. So lag load delivers leading reactive power. Leading reactive power. Is it clear? Okay. Next one more thing. Suppose now let me discuss regarding lead loads. Now tell me, what about lead? So what is the property of lead loads? I am saying it delivers. Normally it delivers reactive power. Delivers means from here it will go like this, right? It will go like this. See, lead load delivers means from here it is leaving, delivers reactive power. Tell me, this reactive power is going towards whom? Towards lagging nature. That means if you want me to say lead load delivers reactive power, what type of reactive power we have to write that? Lead load delivers, this reactive power is coming towards lagging nature, right? Towards L load, towards lagging load. That means lead loads delivers lagging reactive power. That word is very important. So let me write here lead loads delivered. So from here it is leaving. it is going towards lagging nature, it is going towards lagging loads, simply lead loads delivers lagging reactive power. Lagging reactive power. So sometimes they may ask you in terms of lag loads, in terms of asking delivers, they may ask you in terms of absorbs. Absorbs. Now tell me. Suppose instead of giving arrow mark like this, sometimes arrow mark will be like this. Now tell me in this case. So lead load, reactive power, sometimes they will observe. Which type of reactive power is absorbed by lead loads? So it is coming towards whom? Towards C, towards capacitor load, towards leading loads. That means lead loads absorb, lead loads absorb. It is coming towards leading loads. Lead loads absorb, lead loads absorbs, lead loads absorb leading reactive power. Okay, so let me write lead loads absorbs leading reactive power. So if you want me to write similarly, generally if you want me to write in terms of lag means what? Generally inductive loads. So let me please complete the statement. Inductive loads absorbs lagging reactive power. Inductive loads delivers leading reactive power. Both statements are correct only. Capacitive loads, lead loads means what? Capacitive loads. Capacitive loads delivers lagging reactive power. Correct. Capacitive loads absorbs leading reactive power. This is also correct. Is it clear? But here what I wrote here, observe clearly. I wrote here lag loads absorbs reactive power. See, lag is here. These 2 points. Lag loads absorbs reactive power. So I focused this statement. So regarding lag loads point of view, I focused this statement. In terms of lagging, I told this reactive power by default, I am just lag loads absorbs reactive power. Lag loads absorbs which reactive power? Lagging reactive power. That means whatever the controls they are given here, these are by default. I discussed about lagging reactive power. If you want, you can check. Lag loads absorbs lagging reactive power. Lag loads absorbs lagging reactive power. Statement number 1 correct. Now what about note 3? Lead loads delivers. Lead loads delivers. Here, lead loads delivers lagging reactive power. So lead loads delivers. This is by default which type of reactive power? Lead loads delivered. Lead loads delivered lagging reactive power. Lead loads delivered lagging reactive power. This one. I focus this statement. Lead loads delivered lagging reactive power. I don't want to make you confused. Simply regarding machines point of view, whatever the notes, note 2, note 3, note 4 I had given here, I indirectly discussed about lagging reactive power here, but I did not mention lagging or leading. So by default, I discussed about lagging reactive power. Okay, lag loads absorbs lagging reactive power. Lead loads delivers lagging reactive power. Okay, so indirectly by default, I am discussing about reactive power means by default you please take that reactive power as lagging reactive power. So there is from now onwards I won't use words lagging reactive power, leading reactive power. Simply I will be using reactive power. That's it. But examination point of view, they are asking some 1 mark point of view questions. That's why I had given you this table column. Okay. So you may in options suppose regarding lag loads, if he is asking question. If he is asking regarding lag loads absorbs lagging reactive power, statement correct. Lag loads delivers leading reactive power, statement correct. Suppose if he is asking question regarding lead loads delivers lagging reactive power, correct. Lead loads absorbs leading reactive power, that is also correct. So these points are important for examination point of view. So please write, and if you can write, if you want, you can write here exam point of view. But in my discussion, I won't use lagging reactive power, I won't use leading reactive power words. Simply, I will be using reactive power. That's it. That means by default, I'm just focusing on a lagging reactive power. I don't want to make you confused. Simply, I'll be using reactive power only. By default, take it as lagging reactive power. And these statements, four statements, remember for exam point of view, and just write and just keep it away. Don't include these things here in my discussion, coming discussion. So I'll be using normally reactive power only. Lag loads absorbs reactive power simply. Lag loads absorbs reactive power. Lead loads delivers reactive power. Lag loads absorbs reactive power. Since they are absorbing reactive power, lag loads are under excited. Okay. Lead loads delivers reactive power, and they are over excited. Over excited. Is it clear? So please write these four statements for exam point of view, and just remember this node 2, node 3 in terms of reactive power only. Don't include lagging or leading words. Right. See now, in next session, I'll tell you how synchronous motor. I just replaced DME with, in case of alternator, wherever DME is there, I replace with ME. In alternator, wherever ME is there, I replace with the DME. So these things I'll explain once again. This table column I won't erase. It will be like this only by using this table column, and I'm just erasing this portion also. This is important for exam point of view only, but don't remember these four statements for my coming sessions. Just remember these four statements for exam point of view, and so just simply remember in terms of normal reactive power. That's it. That means lag load absorbs reactive power. They are under excited. Lead load delivers reactive power. They are over excited. So just remember that statement is enough. Resistive load neither absorbs reactive power nor delivers reactive power. They are normal excited. Simple. Okay. So just remember this. By using these statements, I can say node 1, node 2, node 3, node 4, and this table column. I'm just going to explain in the next session. Okay, how I got purely ME in synchronous motor, whereas in alternator